Well, our last example is going to be where the coefficient matrix has complex eigenvalues. This one's a little bit trickier, so we're just going to do it with a 2x2, and I think that'll be the way your homework is as well. But let's look at the theorem first. The theorem says complex eigenvalues. If this system of differential equations, where all of the entries of A are real numbers, as they have been for all of our examples, and lambda 1, our first eigenvalue, is a complex number, alpha plus beta I. Alpha and beta are real numbers, so that's a standard form for a complex number. So lambda 1 and k1 are an eigenvalue eigenvector pair. If we get that, then the two solutions that we could simply add together and put a C1 and a C2 in front of them would be these two that we would add together. K1 times e to the lambda 1t, we've seen that before, and the other linearly independent eigenvector and would be K1 with the bar over it, which means the complex conjugate of K1, explain that in a minute if you don't remember, times e to the complex conjugate of lambda 1 times t. Once you get this is trivial. Those two would be the solutions of the differential equation. So as I mentioned, you just put a C1 in front of that, plus put a C2 in front of that, and we've got it. So recall, if you don't remember what a complex conjugate is, if lambda 1 is this number, alpha would be 2, beta would be -3 in alpha plus beta I, that just means that lambda 1 with a bar over it, the complex conjugate, is 2 plus 3i. So you change the sign in front of this, the imaginary portion of this. You don't change the sign on the real number part. Alpha doesn't change. The complex conjugate of this is alpha minus beta I. And if we have alpha minus beta I, then the complex conjugate is alpha plus beta I. And this, we have a vector. We have two entries in the vector. If K1, if that happened to be an eigenvector, or even if it's not, the complex conjugate is, just take the complex conjugate of each term. Remember, 5 is 5 plus 0i. So here I'm going to write 5 minus 0i. But 5 plus 0 is 5 minus 0 is just 5. Here I'll change it from 1 plus 5i to 1 minus 5i. So this is just to remind you what complex conjugate means. And I'm going to make a comment in here to make life easier for you. We will leave the solution in the form something like I already said. C1 times this eigenvector times this plus C2 times that. There's a more desirable way to write it where the functions used, like e to the lambda 1t, that's a function of t, but lambda 1 is a complex number. We would like to use real valued functions and then just have the constants be complex numbers. It turns it in from having things like e to the lambda 1t into having things that look like sine lambda 1t and cosine lambda 1t, and the constants, multipliers in front of that, the C1 or the C2, would be complex numbers. We're not going to take that extra step. So our solution is going to look something like summing up two things like this. Okay, well here is our system of two equations. X prime is a function of xy, y prime is a function of xy. As you can see, our coefficient matrix is 6, -1, 5, 4. And just I'm reminding you again, the characteristic polynomial is the determinant of the coefficient matrix A minus lambda I. That would be the characteristic polynomial on the left side. When you set it equal to 0, it gives you the characteristic equation. So what does that give us? Remember, a minus lambda I means you're only changing the diagonal entries and you're subtracting a lambda from it. So that would give us the determinant of 6 minus lambda, negative 1, 5, 4 minus lambda, times, oh, I'm sorry, getting ahead of myself trying to find eigenvectors before we have found the eigenvalues. Just set that equal to 0. It'll be a polynomial in lambda, solve for lambda, and we'll get our two eigenvalues. And just to make a note, when you have a polynomial with real valued coefficients like we're guaranteed to have because this is a real valued function, whenever you get a complex solution, that means also, or a complex root, a complex solution to this, it means they're going to come in complex conjugate pairs. If 8 plus 10i is one solution, 8 minus 10i will be another solution. And we'll see that in a minute. Okay, so what does this mean? This means that 6 minus lambda times 4 minus lambda, that minus negative 1 times 5 equals 0. And that means that I'm going to FOIL this out. 24 minus 6 minus 10 lambda plus lambda squared plus 5 equals 0. And that implies that lambda squared minus 10 lambda 24, 5 plus 29 is equal to 0. So we can't factor this in our heads. At least I don't think you can. So we're going to plug it into the quadratic formula, and we're going to get, and maybe I'll start over here to the left to save some room, the solution to this is lambda equals negative b plus or minus b squared is 100 minus 4, a, which is 1, c, which is 29, all over 2a, which is 2. So to conserve some room, I'm going to go to the right and then come back down here. I'm going to break that up into two fractions. 10 over 2 is 5, plus or minus 100 minus 116. 100 minus 116. So this is equal to 5 plus or minus radical negative 16. You plot the negative sign and put an I in front, and radical 16 is 4. So we get that lambda is equal to 5 plus or minus 2i. So that's like saying my alpha is 5 and my beta is 2. We have alpha plus or minus beta I. Complex conjugate pair, those are exactly the two eigenvalues. Now let's find the eigenvector, and this does get a little bit weird. Now find the eigenvector. Vector associated with 5 plus 2i. You could use 5 minus 2i if you wanted as well. The solution will be equivalent. So we have to say a minus 5 plus 2i, a minus lambda I, times k1 equals 0. So, and maybe I'll make it obvious that this is the 0 vector. It's the 2 by 2 0 vector. So now, what is this matrix? A, this is an A. So from the diagonal, we're going to subtract 5 plus 2i. So here's A. So that matrix is going to be 6 minus 5 plus 2i, and then a negative 1, and a 5, and 4 minus 5 plus 2i. And we're going to multiply that by k1, and we're going to get 0. All right, so 6 minus 5 is 1 minus 2i, negative 1, 5. 4 minus 5 is a negative 1, and that's a minus 2i. All right, we're going to have to do some row reduction, Gaussian elimination, and turn this 5 into a 0. All right, let's see what happens here. I'm going to get the matrix 1 minus 2i minus 1, 0. 5, negative 1 minus 2i, 0. And we have to row reduce. So I need the 5 to become a 0. So my multiplying factor is going to be 5 divided by 1 minus 2i. So I'm going to say row 2 minus 5 over 1 minus 2i, row 1. Looks like a tough row reduction just because of the complex numbers, and we have a fraction with complex numbers in the denominator. Okay, what's that going to give us? That's going to give us, the top row is not going to change. I know it's going to give us a 0 there. That's why we chose that as the multiplier. If you multiply 5 over 1 minus 2i, that cancels and leaves you with just the 5. And for the next one, I'm going to write it down. Actually, I'm gonna do a negative 1 minus 2i minus 5 over 1 minus 2i times negative 1. Well, this is all going to simplify to be a 0. Let's see, negative 1 minus 2i. That's really plus 5 over 1 minus 2i. Okay, that's equal to that. Well, in my scratch paper, I'm going to write down what 5 over 1 minus 2i is equal to. This is going back to pre-calculus probably, if you haven't had complex analysis recently. Well, I'm going to multiply this top and bottom by 1 in the form of the complex conjugate of 1 minus 2i. So let's go 1 plus 2i over 1 plus 2i. And we would get, on the bottom, if you FOIL this out, you're going to get 1 squared plus 2 squared, which is 5. The I terms cancel out. That's a 2 right there. And on top, we get 5 plus 10i. So that cancels out to be a 1 plus 2i. So we have negative 1 minus 2i plus 1 plus 2i, and we get 0. So all of that work was just to show that we get this. That's our reduced matrix. The first entry is 1 minus 2i, and the other one is negative 1. I'm going to erase this scratch work here. Okay, so remember what we've got here. This is the little k1 column and the little k2 column, where k1, big K1, is that. So I'm going to say that 1 minus 2i times k1 minus k2 is equal to 0. That's just the equation that we get from the very, very top row. So we get an infinite number of equations. And I think what I'm going to do is just say that this means k2 is equal to, if I added it to that side, 1 minus 2i times k1. And for simplicity, let's see, I think I'm going to choose k2 to be a 1. Choose, didn't have to do this, we could choose anything we want actually. Choose k2 equal to 1, so k2 is a 1, that means k1 is 1 minus 2i. So that gives me my k1 is equal to 1 minus 2i, 1. So now we're just going to use the theorem. The theorem, just as a reminder of what we need, I'm going to say that k1 is that implies that k1 complex conjugate is almost the same. It's just 1 plus 2i and 1. And we also have lambda 1. What did we choose? We used 5 plus 2i. Implies that complex conjugate of lambda 1 is 5 minus 2i. So we are going to, I'm going to write the solution down because we can just use that theorem. And I'm going to write it in black. Maybe I have not enough room to write it down here. Using the theorem, we've got the solution being x is equal to c1 times k1, 1 minus 2i, 1, e to the lambda 1i. Lambda 1 is 5 plus 2i. I said I instead of t. The lambda 1t. And the second term is going to have a c2, and it's going to be this k1's complex conjugate, e to the 5 minus 2i t. And that is the solution. So it's not too bad. It's just the arithmetic with complex numbers that you might not be used to. And again, there's a way using Euler's formula, e to the I theta equals cosine theta plus I sine theta, where we can make the functions, like this function, we would turn it into sines and cosines of real numbers, and only the constants out front would be complex numbers. All the functions would be real. So when you're doing the homework problems, you may come up with a solution that looks like this. If it's an odd number and you're checking the answer in the book, it may look completely different for the reason that they simplified it. I don't want to say simplified it, but they wrote it in a way they had sines and cosines, real valued functions, instead of things like e to the 5 plus 2i. So it's going to look much different. Just remember that when if you're checking the answers in the back of the book. And that is the last example we'll do of this section.